Okay, in the previous video, we proved a theorem on extending K monomorphisms, and then before we gave the proof, we applied it to this example of extending the inclusion of Q adjoint alpha into this splitting field of T cubed minus 2 to construct an element of the Galois group. Okay, so what we're going to do here is we're just going to make that rigorous in general. So we're going to extract from the example a general fact. So suppose that we have a finite normal extension. So again, think in your mind splitting field. And alpha and beta in L are zeros of the same irreducible polynomial. Not just a polynomial. It needs to be irreducible. Alpha and beta need to be conjugates. So that's all this is telling us, is that alpha, beta are conjugates. It must be conjugates. So they're the zeros of an irreducible polynomial p over k. Then there exists a k automorphism. Automorphism sigma of L such that sigma of alpha is equal to beta. Again, we saw that in that one example that we constructed a Q automorphism that set alpha to omega alpha. They were both roots of the same irreducible polynomial t cubed minus 2. Let's prove this. It will not be difficult. Since alpha and beta are conjugates, there exists a K isomorphism tau from K adjoint alpha to K adjoint beta. Right? There exists an isomorphism between these that that fixes K. Let's actually not call it tau. Let me call it iota or J. Let me call it J. Let's let tau be include after doing J as a function from K adjoint alpha to L. So we do J, and then we say, hey, let's then include that into L. That's all that tau is. Then tau is a K monomorphism. It's a K monomorphism because it does not mess up K, and it's clearly a monomorphism. By the theorem that we proved in the previous video, there exists sigma from L to L, a K auto, such that sigma restricted to tau, it's restricted to K adjoint alpha, is tau. Okay, so we've applied the theorem. Then there's this last condition. We don't only have to construct a K automorphism, it also needs to send alpha to beta. So let's say and sigma of alpha. Alpha is in K adjoint alpha. So that's tau of alpha. And what's tau of alpha? Tau of alpha is do J and then include into L. What does J do? J, sorry, I didn't clarify here. When they're conjugates, alpha goes to beta. So J sends alpha to beta, and then tau does that and then includes into L. So this is just going to be a beta. So this is as alpha is in K adjoint alpha. And that's what we wanted to show. So what we're learning, that's the end of the theorem, is that when you have a splitting field, let's suppose for a second that the splitting field of an irreducible polynomial, so alpha and beta are roots of the same irreducible polynomial, and we just adjoin the roots of the same irreducible polynomial, then there's always an element of the Galois group that sends any root to another root. Okay? So if L is sigma F is a splitting field where F is irreducible, must be irreducible for what I'm about to say to be true, then there exists for any two roots of F an element of the Galois group, sending one to the other. We don't have to actually write down any automorphisms, which is very difficult. We just know from this proposition now that whenever we have two roots, we can send one to the other. It doesn't mean that we're interchanging them. We just know we can send one to the other.